planet and its moon gravitationally attract each other. Rank the forces of attraction between the pair from greatest to least. So we have two things involved here. One are the masses, and the other one is the distance between it. And so treating A as sort of the normal standard, because you just plug in big G times M over D squared. For B, you're doubling one of the masses. And actually for C also, you double one of the masses. And so you have an additional 2 in the numerator. So that's the force of attraction in B and C is going to be twice that of A. D, you double a mass, but you also double one of the masses, but also double a distance. So that puts an extra 2 in the numerator and an extra 4 on the denominator, because that 2D, that whole thing is squared, which makes it 4 times D squared. And so B and C should be equal. A would be next, and then D is the smallest because, again, that fraction you have a 2 over 4, which is 1/2. 46, consider the light in multiple candle flames, each of the same brightness. Rank the light that enters your eye from the brightest to the dimmest in the following situations. And so, very similar to what we had before, you have, every time you light a new candle, you have that much more brightness. So if we looked at just candles, ignoring distance, 3 candles is brighter than 2 candles, brighter than 1 candle. Matter of fact, 3 candles is 3 times 1 candle and 1.5 times 2 candles. But the distance, because the light travels out in a sphere, you get that 1 over r squared relationship. And so 3 candles from 3 meters away, you end up with an extra 3 in the numerator and a 3 squared in the denominator. So that's 1/3. 2 candles, 2 meters. So that is... So you end up with 2 in the numerator from the 2 candles, and then 2 squared in the denominator, or 1/2, and then 1 candle, 1 set of distance, or distance of 1 meter. You have 1 over 1. So in terms of brightest, 1 candle from 1 meter is brighter than 2 candles from 2 meters, which is brighter than 3 candles from 3 meters. This is very similar to what we just did, where instead of mass, we have have number of candles in the numerator, and the distance is still squared in the bottom, because again, the light travels out in a sphere, and the surface area of the sphere is 4 pi r squared. That's where the r squared comes from. 47, pretend you fall into a board, a whole board, completely through the Earth, discounting friction and rotational effects. Rank your speeds. All right, so this goes back to the gravitational pull, that if you're outside the planet, the formula is, as was written, the big G M1 and 2 over D squared or R squared. And so graphically, it would look like it's a 1 over R squared relationship, which looks like that. So if this is the radius of the planet, so we picturing a graph. Actually, there's a graph on a page, page 172. So and then once you are inside the Earth sphere or the planetary sphere, assuming solid and uniform density, that it's directly proportional. So when you're in the center, the gravitational pull is 0 because you're pulled equally in all directions. And it's linear until you get to the surface, and it becomes a 1 over r squared relationship. So in terms of speed, your speed is going to be greatest at B, because you are pulled towards the center of the Earth, and you're going faster and faster and faster, and then you pass B, and then you start slowing down. Very similar to if I took a slinky and I pulled it down, and it would start oscillating back and forth. It is fastest when it passes through the equilibrium point, and then it slows down as it gets to the maximum extension, and slows down as it gets to maximum compression. Matter of fact, this can be modeled by that when we get into chapter 19, I'm pretty sure it is 19, we can talk about this slightly differently, but this would obey Hooke's law, which I've mentioned briefly in class, I believe, at this point. So speed, the farther away you are, the slower you are. So D would be the slowest. I guess we're ranking from greatest to least. So B is the fastest. A and C, assuming those are equidistant from the center, are the same, and then D is the slowest. I hope D is the slowest, because that's when you pop out on the other end, and then you start working your way back. Acceleration, on the other hand, is the opposite, because the force is the greatest when you're at the surface of the Earth, and it decreases as you get closer to the center. And so The acceleration is greatest at D, tied at A and C, and then B, it is the lowest, because at B there should be no acceleration. That's when your velocity peaks and starts working the other way. Now, just as a side fact, and this might come up in class also, but if you could actually do this, some people have actually gone through and calculated what it would be, and potentially we could do this in class when we get through chapter 19 or 20. Definitely could do it in 151 and 251. But it would take somewhere around 40 minutes to actually go from pole to pole, given, ignoring all the effects that they mentioned. Problem 48. Rank the average gravitational forces from greatest to least between the Sun, Mars, Sun and Moon, Sun and Earth. Sun and the Moon. It's our Moon. All right, so let's just treat Sun and Earth as sort of the standard right there. There's a certain amount. The Moon is roughly the same distance from the Sun as the Earth is. It does fluctuate, but there's not a significant difference, considering the mass of the Moon is about 1.2% of the mass of the Earth. That definitely would offset any small fluctuation in distance. And so Sun and Earth gravitational pull is definitely greater than Sun and Moon, just because the mass of the Earth is so much greater, almost 100 times greater than the mass of the Moon. Sun and Mars is a little bit trickier. You know that Mars is smaller than Earth or less massive than Earth, and it's farther away, so definitely Sun and Mars has less of a gravitational pull than Sun and Earth. However, Sun and Mars versus Sun and the Moon. Well, Mars is about 1.5 times of the distance from Sun to Moon. So Sun to Moon is 1 astronomical unit. Sun to Mars is about 1.5 astronomical units. The mass of Mars is about 10% of the mass of Earth, and the Moon is about 1.2%. So the mass of Mars, very roughly, is 9 or 10 times larger than the mass of the Moon. So we have in the numerator this additional comparing mass in Mars and Moon, 9 times more for Mars, and the distance is 1.5 times greater. But if you square 1.5, you get 2.25. So 9, which is 9 or 10, divided by 2.25 is definitely bigger than 1. In other words, Sun to Mars is greater than Sun to Mars gravitational pull is greater than Sun and our Moon. I believe the solution says CBA, and it should be CAB as the order. Number 49, rank the microtidal forces on your bodies from the greatest to least produced by, and then it gives some choices here. Well, the Earth definitely has the greatest pull there. I can't jump up. I'm not going to the Moon and Sun when I jump towards them. So Earth has the greatest gravitational force on us, and Moon actually is closest. Yes, the mass of the Sun is incredibly much greater than that of the Moon, but the Moon is so much closer. We experience tides because of the Moon's how close the Moon is. We don't experience tides because of the Sun. Not directly. The Sun might cause some heating issues, which cause a change in the fluid, but that's several times removed. So BAC is the order for number 49. And that's it for Think